All right, guys, in this video, we're going to be looking at how Le Chatelier's principle influences our Q and K, or reaction quotient and equilibrium constant. And we got three multiple choice questions. So here's one. We've got a reaction. Which of the following changes will increase the amount of NO2 in the equilibrium system represented by the equation above? So we have a reaction. We're assuming it's at equilibrium, and we want to increase the amount of NO2. NO2 being a product. So we want to look at one of these four options and see how we can make more product. Without even looking, some options we can do to actually make more NO2 is we can increase the amount of CO2 or NO. So if that's an answer choice, by increasing one of those, we will then increase the amount of NO2 because Le Chatelier's principle states that it's got to fix the ratios of the concentrations of the reaction. So if we increase the amount of reactants, it has to shift to the right forward direction to make more product. So that could be a choice. We don't know if it's endothermic or exothermic, so we can't use those as options to actually determine if changing the temperature will make more product or reactant. So if those are answer choices, we can't even select those because we don't know if it's endothermic or exothermic. Another option is removing CO. If we remove some carbon monoxide gas, then we have to shift the direction of the reaction towards products to make more carbon monoxide. To fix that ratio of concentration, that will just automatically increase the amount of NO2. So those are my three choices without even looking at my answer choices. Okay, so we'll start from the bottom going up. D, decreasing the volume of the reaction vessel. All right, or increasing the volume of the reaction vessel. Now, this works if we have different amounts of gaseous molecules on each side. In this example, we have two molecules of gases on this side and two molecules of gases on this side. So increasing and decreasing this volume is not going to change it. Let's say we had one or maybe we'll say two over here and three over here molecules. Maybe there's two carbon monoxides. I don't know. If we increase the volume of the reaction vessel, that would shift it towards the products. So then C could be a possibly correct answer, but otherwise it's not going to be. If we decrease it, it would shift to the reactants. So if we were at a question that asked for the reactants and we had 2 versus 3 molecules on each side, then D would be correct. But in this case, because we just have 2 molecules of gas on each side, changing the volume is not going to matter. Okay, B says removing carbon dioxide from the system, so remove it here. That's going to do the opposite of what we want. That's going to force the reaction towards the reactants and make more carbon dioxide and more nitric oxide. So B is not right, and the only option left is A, and it is one of the things we talked about earlier. If we remove carbon monoxide, it has to shift to the right to make more products, thereby making more NO2. So A is definitely the right answer. Okay, looking at another equilibrium question in Le Chatelier's. So we have a reaction. We're given the Kp. A mixture of NO2 and N2O4 is placed in a glass tube and allowed to reach equilibrium, as represented above. Which of the following statements best explains why the contents of the tube containing the equilibrium mixture turned a lighter color when the tube was placed in an ice bath? So there's a lot of information we need to look at and unpack here. So we have this reaction. N2O4 is colorless and NO2 is brown. And it said when we put it in an ice bath, it turned lighter. That's a key indicator that the reaction went in the reverse direction. It went from products to reactants. So let's look at our answer choices. First, let's look at C and D. The ice bath lowered the activation energy, or the ice bath raised the activation energy? Now remember, activation energy is just the energy required to start a reaction. Okay, there's no indication for Le Chatelier's principle. It doesn't matter. The activation energy can be whatever it wants. It's not going to determine if it's going to get shift to the left or shift to the right. So C and D are not even possible answers. So right off the bat, we've narrowed it down to at least A and B. So now it's just asking us, is this exothermic or is it endothermic? Okay. Well, let's look at if it's at exothermic first. So if it's exothermic, we could say that the heat is going to be on this side of the reaction as a product, heat. And if we lower heat, because we put it in an ice bath, which way should it go? Well, actually, it should go towards the product side. Think of it as a product itself, just like we did right here when we removed carbon monoxide, it shifted it towards the products. So same thing here with an exothermic. If heat's like acting like a product, we need the heat for the reaction to go, right, in this direction. If we're removing that heat, it should push it to make it more products, which means it should actually get darker. So it's not going to be exothermic, it's going to be the opposite. The reaction is actually endothermic, with heat being a reactant. Sorry, it's going to be over here. And by cooling it down, we have to then force it to the reactants. So that's how we can use endothermic, exothermic to determine if we're going to create more product or reactant. So it's based on if it's exothermic, endothermic. It's going to be based on if you increase the temperature or decrease the temperature. And finally, this one, same exact idea, but we're going to involve a little math here. So we've got a reaction, and we've got a KSP. KSP is solubility product, so that means I'm dealing with the salt, and I have a solid salt, and it's going into 2 ions. And the dissolution of this in water is represented above. A 20 milliliter sample of 1 × 10⁻⁴ molar barium nitrate is mixed with 80 milliliter sample of 1 × 10⁻⁴ molarity of sodium carbonate. Which of the following predicts and explains the outcome? Okay, so there's a lot of moving pieces here, but let's talk about what's happening. So we have a solution of barium nitrate. Oh, it's just, yeah, okay. Barium nitrate. And another solution of sodium carbonate. Okay, and the ions that we actually care about are the barium and carbonate. So when these two mix with each other, only the barium and the carbonate matters. And what I guess I should do also is know that KSP is the concentration of barium and carbonate, and it's just multiplied by each other. Okay, that's also how we solve for the QSP. Same exact thing. So I need to know the concentrations of the barium and the carbonate. Well, remember when we combine two things, we're actually going to be changing the molarity, because in this this sample of 20 milliliters, we have that concentration. But when we combine it with the other one, we're going to be increasing the volume of it. So we have to do boom, boom. It's been a while, but we are going to boom, boom here. So we take 20 milliliters. And we'll have to multiply it by its concentration, 1 × 10⁻⁴ molarity. Now, I can't directly multiply it like that, right? I should. Well, actually, I think it'll be fine as long as we keep the correct units of molarity. But I'm going to do it with liters. So this would be 0.02 liters. And the new volume will be 80 plus 20 milliliters, which is 0.1 liters, and then I want the new molarity. Okay, so then all I got to do is 0.1 liters on each side, and I can get the new molarity. So the new molarity of the barium, so my barium concentration is 0.02 times 1 × 10⁻⁴ divided by 0.1. And I get 0.0002 molarity from my barium concentrate. Okay, we'll do the same thing for my carbonate concentration. I have 0.08 liters, and I have to multiply that by 1 × 10⁻⁴ molarity. That's equal to 0.1 liters times the new molarity divided by 0.1 on each side. That cancels out. So then the new concentration of the CO3 2+ is equal to 0.00008 molarity. Okay, so just to recap what I've done so far, I know this is my KSP, which is the same thing as my QSP. Okay, so if I want the concentrations of the barium and the carbonate, so I had to boom boom to solve for those ones. Now I can plug it in. So I go 0.0002 times 0.00008. Sorry, running out of space here. If you do that in your calculator, you're going to find that the answer is 1.6 times 10 to the negative 9. So that is my Q. It's my Q because I'm not at equilibrium. Notice my KSP is 8.1 times 10 to the negative 9th, and my Q is 1.6 times 10 to the negative 9th. So if you were to just do this part and do it correctly, you should actually be able to narrow it down to B and D. A and C are not right. They give them incorrect Q values, so it has to be B or D. Now, the question is, will a precipitate form or will a precipitate not form? Now remember, it's all based on the QSP. The KSP and the QSP, you got to combine them both, right? But the QSP tells us the saturation. That's the constant it has to reach before it starts to produce product or reactant in this case. We want to produce a precipitate. So what is my Q compared to my K? Well, my Q is less than my K. This number is smaller than my K. Since my Q hasn't even reached the K, a precipitate will not form. It won't start producing that precipitate. It's just going to be ions at this point. So the answer for this one is a precipitate will not form because the Q is 1.6 times 10 to the negative 9th. Okay, hope that was helpful.